The greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. It is not clear that intelligence has any long term survival value. One cannot really argue with a mathematical theorem. It is a waste of time to be angry about my disability. One has to get on with life, and I haven't done badly. People won't have time for you if you are always angry or complaining. I relish the rare opportunity I have been given to live the life of the mind. But I know I need my body, and that is will not last forever. Hi guys, it seems an interesting avenue that is worth further exploration, and I am sure we will see further exploration. Hawking radiation. Hawking now embraced the idea that thermodynamics played a part in black holes. Anything that has entropy, he reasoned, also has a temperature, and anything that has a temperature can radiate. His original mistake, Hawking realized, was in only considering general relativity, which says that nothing, no particles, no heat, can escape the grip of a black hole. That changes when quantum mechanics comes into play. According to a quantum mechanics, fleeting pairs of particles and antiparticles are constantly appearing out of the empty space only to annihilate and disappear in the blink of an eye. When this happens in the vicinity of an event horizon, a particle antiparticle pair can be separated. One falls behind the horizon while one escapes, leaving them forever unable to meet and annihilate. The orphaned particles stream away from the black hole's edge as radiation. The randomness of quantum creation becomes the randomness of heat. I think most physicists would agree the Hawking's greatest contribution is the prediction that black holes emit radiation, says Sean Carroll, a theoretical physicist at the California Institute of Technology. While we still don't have experimental confirmation that Hawking's prediction is true, nearly every expert believes he was right. Experiments to test Hawking's prediction are so difficult because the more massive a black hole is, the lower its temperature. For a large black hole, the kind astronomers can study with a telescope, the temperature of the radiation is too significant to measure. As Hawking himself often noted, it was for this reason that he was never awarded a Nobel Prize. Still, the prediction was enough to secure him a prime place in the annals of science. And the quantum particles that stream from the black hole's edge would forever be known as Hawking radiation. Some have suggested that they should more appropriately be called Bekenstein's Hawking radiation. But Bekenstein himself rejects this. The entropy of a black hole is called Bekenstein-Hawking entropy, which I think is fine. I wrote it down first. Hawking found the numerical value of the constant. So together we found the formula as it is today. The radiation was really Hawking's work. I had no idea how a black hole could radiate. Hawking brought out that very clearly. So that should be called Hawking radiation. Theory of everything. Bekenstein-Hawking entropy equation is the one Hawking asked to have engraved on his tombstone. It represents the ultimate mashup of physical disciplines because it contains Newton's constant, which clearly relates to gravity, Planck's constant, which betrays quantum mechanics at play, the speed of light, the talisman of Einstein's relativity, and the Boltzmann constant, the herald of thermodynamics. The presence of these diverse constants hinted at a theory of everything, in which all physics is unified. Furthermore, it strongly corroborated Hawking's original hunch that understanding black holes would be key in unlocking the deeper theory. Hawking's breakthrough may have solved the entropy problem, but it raised an even more difficult problem in its wake. If black holes can radiate, they will eventually evaporate and disappear. So, what happens to all the information that fell in? Does it vanish too? If so, it will violate a central tenet of quantum mechanics. On the other hand, if it escapes from the black hole, it will violate Einstein's theory of relativity. With the discovery of black hole radiation, Hawking had pit the ultimate laws of physics against one another. The black hole information loss paradox had been born. Hawking staked his position in another ground, breaking an even more continuous paper entitled Breakdown of Predictability in Gravitational Collapse, published in Physical Review D in 1976. He argued that when a black hole radiates away its mass, it does take all of its information with it, despite the fact that quantum mechanics expressly forbids information loss. Soon other physicists would pick sides for or against for this idea in a debate that continues to this day. Indeed, many feel that information loss is the most pressing obstacle in understanding quantum gravity. Hawking's 1976 argument that black holes lose information is a towering achievement, perhaps one of the most consequential discoveries on the theoretical side of physics since the subject was invented, says Raphael Bosso of the University of California, Berkeley. Concession. By the late 1990s, results emerging from string theory had most theoretical physicists convinced that Hawking was wrong about information loss. But Hawking, known for his stubbornness, dug in his heels. It wasn't until 2004 that he would change his mind. And he did it with flair, dramatically shown up at a conference in Dublin and announcing his updated view. Black holes cannot lose information. Today, however, a new paradox known as the firewall has thrown everything into doubt. it is clear that the question Hawking raised is at the core of the quest for quantum gravity. Black hole radiation raises seriously puzzles we are still working very hard to understand, says Carroll. It is fair to say that Hawking radiation is the single biggest clue we have to ultimate reconciliation of quantum mechanics and gravity. Arguably the greatest challenge facing theoretical physics today. Hawking's legacy, says Basso, will be having put his finger on the key difficulty in the search for a theory of everything. Hawking continued pushing the boundaries of theoretical physics at a seemingly impossible pace for the rest of his life. He made important inroads towards understanding how quantum mechanics applies to the universe as a whole, leading the way in the field known as a quantum cosmology. His progressive disease pushed him to tackle problems in novel ways, which contributed to his remarkable intuition for his subject. As he lost the ability to write out long, complicated equations, Hawking found new and inventive methods to solve problems in his head. Usually, he reimagining them in geometric form. But like Einstein before him, Hawking never produced anything quite as revolutionary as his early work. Hawking's most influential work was done in the 1990s when he was younger, says Carroll. But that is completely standard even for physicists who aren't burdened with a debilitating neuron disease. Black holes may not destroy all information about that they are originally made of, according to a new set of quantum calculations, which would solve a major physics paradox first described by Stephen Hawking. But it seems an interesting avenue that is worth further exploration, and I am sure we will see further exploration. Thanking you very much. You listened eagerly, patiently, and took interest. Please like the video, share it, and subscribe it. Thanks again a lot.